So, we will continue with our mooring systems in this lecture. So, as I have last class, as I have told you, there are three types of analysis that we have to do. So, in the mooring systems, which are very important for offshore structures. The reason is they are stationary at one place and they have to encounter the motions from the waves. So, mooring system, there are three types of analysis. First, what you do that we will be doing in this class is static analysis. Then you have quasi-static, and the last one is your dynamic. So, all this has to be done. Now, coming to the static analysis part, that is your mooring chain actually assumes the configuration of a catenary wire. So, it is actually a catenary wire. Some of you have done the mechanics also, but let us see similar mechanics out here. So, here is our water line. So, you take a reference on the mean sea level. So, this is your water plane, or you can call it this mean sea level, whatever it is. Now, we will make some assumptions in order to simplify matters. So, this is your x positive direction and x positive direction of z axis, and you assume your boat or platform to be out here. Let us say that the deck is more or less at the mean sea level or a little bit away from it. So, this will be the horizontal part of your cable tension. So, this is TH. Now, your mooring cable actually is wound in a windlass, or in the semi-submersibles you call it a mooring winch. So, the mooring winch will exert a force in this direction, you call this as TW or T winch, and this will make an angle of say phi w with the water plane. Okay. So, now let us see your seabed actually is the height of the seabed, say let us take here. Now, you remember the sign of the z axis. So, this is the x, z and y is on this. So, h, you take this as h. Now, your mooring cable actually assumes the shape of a catenary. So, you draw a catenary wire rope. Now, the static analysis that I will be doing here is quite simple, but in the actual case it is not so. Now, what happens is that the mooring line will lie to some extent on the seabed like this. Now, it will take a certain angle from this point, and this is your anchor point. Say this is your anchor point. Now, this distance you write as x b. So, this is the shape of your mooring line. Okay. Now, mooring line it assumes the shape of a catenary. It is never a steel, this is a steel cable. So, it will never be taut or in one straight line. It assumes the shape of a catenary, and a large portion of the line will be lying flat on the seabed, as you can see. Now, what happens if you exert a force of TW on the boat in this direction? You will exert a horizontal force in this direction. So, anchor line tension is always horizontal, as you can see from the diagram. Anchor line tension is always horizontal, it is never in one particular direction away from the seabed. So, now when you want to lift this anchor, So, this your semi-submersible must what is called ride the anchor, that is it is going to wind the chain cable and then it has to come over the this H and then again it has to come over anchor and then you lift it up. You can never lift a anchor in this mode. So, that is what it is called ship riding anchor. And when you drop a anchor, so these are common is a ship parlance, they say weighing anchor. When you drop the anchor, they say you weigh your anchor, weigh anchor, that is a term. And the other term is when you lift the anchor, it is called ship riding anchor. So, these are marine sort of marine engineering terms. The captain of the ship will say you weigh your anchor, that means you drop your anchor, and if you want to say, so when the anchor is dropped at this point, ship will not come stop at this point. So, it will continue to go in the horizontal direction. So, that is the point that you come here. So, it is acted upon by what is called ship is always acted upon by a drift force. So, this drift force actually comes on the anchor. I do not know drift force calculation ship motions actually will be doing. So, anyway, so now you take a portion of the anchor line, say this is your tension is let us say this is the tangent to the catenary. So, here you will find that this is your tension is tangent and this makes an angle of, at this juncture let us say this makes an angle of phi with the horizontal. So, that means the wire rope is supported by TH in this direction and T0 in the opposite direction, and part the TW will be in the vertical direction which is supporting the weight. So, this will be T cos phi, and obviously, the other one will be T sin phi. Now, there are certain assumptions which you have to make before I draw the free body diagram. Assumption number 1 is seabed is horizontal. Otherwise, this T0 will not be horizontal, then you have to take a component of T0. So, here you write this is your anchor. Follow. Now, number 2 is cable. To make our problem simple, you assume cable is in vertical plane. Coinciding with XZ plane. Anyway, so this actually we are assuming, otherwise you have to take components on the XZ plane, which let us for the present let us ignore. Now, number 3 is bending stiffness of cable line. Now, we are making static analysis. So, right at the top you write static analysis. So, these are not to be confused with quasi-static or dynamic analysis. So, you do not make any dynamic effects. Dynamic effects ignored. So, before we proceed in the calculation, that is with the free body diagram. So, next try to draw the free body diagram. So, you make these assumptions. Now, let us take a portion of the chain cable, say at this point. So, in your magnified form, you draw the free body diagram of a portion of the cable. Say your cable is having a curvature like this. Now, if it is having a curvature, that means the horizontal component at the top of the element, let us take an element of a cable, say let us take it like this. Then what are the forces acting on this? Now, this is your cross sectional area of the cable. So, your tension out here will be how much? So, this will be T plus dt if your tension out here is T. So, there is a change in the tension T plus dt, not only in the magnitude, but also there is a change in the direction as well. Now, direction actually I have drawn this horizontal, and the phi will become 0 in this case. I think let us make it more. You keep a certain angle out here for your problem. Just modify the diagram, or you just draw another diagram, because in this diagram the T is becoming horizontal. Now, in this case, let us assume a direction of T. Now, the direction of T is normal to your cross sectional area. So, this is your T, and this will be your this T plus dt. So, there will also be a change in the angle because of the shape of the catenary. Now, angle out here, this you take the horizontal line. So, angle you write phi plus d phi. This is phi plus d phi, and this one you write as phi. So, at the top end of the cable, the tension is T plus dt, angle making with the horizontal is phi plus d phi, down below is phi and T, fine. Now, there are in the free body diagram, there are other forces. So, this is your free body diagram. Now, what are the other forces? Now, because of the action of your tension, what is happening to the length of the cable? Because this is a wire, so you are stretching it. So, that means if your original length is ds, then this has become, as a result of the application of T, this will change. So, this will become how much? that is your strain in the line. So, you find out the strain. So, your stress is, say, T divided stress in the cable line is how much? Stress is equal to T by A. So, now you find out the elongation from your modulus of elasticity. So, this will be T over A E multiplied by ds, if your ds is the original length. So, this is the amount of elongation. So, your length has become ds plus T over A E multiplied by ds. So, that is the length of your cable. Now, the horizontal direction, this one you take this as dx, and this one you take as dy. Sorry, not dy, what we have said, the direction is z. So, this will be dz, and this one will be dx. So, what we have to find out is from the equation or static equation, you find out T and the length of the cable line. You have to find out ds. So, this is our situation. Now, what are the other forces acting at the ends? Now, you write before we other forces are the hydrodynamic forces. So, the tangential component of the hydrodynamic force, you write this as F, and normal to it you have another force which is called the drag force or D. So, these are the hydrodynamic forces. So, before we analyze this, you write D is hydrodynamic drag force. Actually, in our analysis you will find that since our equations will become more complicated, you have to neglect the hydrodynamic forces, but the hydrodynamic forces are quite substantial. So, hydrodynamic drag force. Now, this force is denoted per unit length. So, this is per unit length. So, total force will be D multiplied by the length of the cable line. Now, F is called hydrodynamic, sorry, D you write drag force, this is normal to cable line. The other one is, say, a hydrodynamic drag force, or rather simply this one is tangent, this is also per unit length, tangential to line. Now, weight, the other portion is W is the chain weight. So, this is weight per unit length of cable line in water. Now, this you note is not in air. So, that means we are taking the buoyancy also into consideration. So, that is the net weight actually, weight in air minus the buoyancy. So, this force is actually acting vertically downwards. If you take out here, so the force that will be acting downwards at this point is W multiplied by ds. For extension, you for this weight you leave it as it is. So, now how much you get? So, A is your cross sectional area of cable. Now, you take the components of these forces in the horizontal and also in the vertical direction. EU is your modulus of elasticity. What other is T is, this is called line tension. So, this is the very simplest analysis that we are doing. Actual analysis is not all that simple. So, now this force is acting. Now, if you take this line to the same out here, so what is the change in the angle at this point? Now, if you take component of force, you do it either in along this line and normal to this line you take the component. So, obviously, this angle is d phi. So, if this was your phi angle, this angle, so the change is d phi. Now, you take component of t plus dt along the line of t. Now, about along this cross section, what are the other forces acting? So, your tension is acting on both the faces, say on the downward face, say this is you can say at A and this is your B. So, what are the other forces acting? Now, for the convenience of your calculation, you take, so you refer to the diagram which we have started with. So, this is the diagram. So, you are doing, say you have taken an element out here. So, we are doing our analysis say at this particular point. Further. So, now you tell me what are the other forces which are acting. Now, here you write this Z from mean sea level. Now, there is a certain, and this will be, and this point is actually there is a correction, you write this as Z plus dz. This point which is above the point A at a higher elevation. The reason we will come to in our analysis to make it simple, you write this as Z plus dz. So, now you tell me what are the buoyancy forces. So, buoyancy forces at A will be, since Z is negative, you write this as minus rho g Z A. So, this is buoyancy force. Buoyancy force at cross section, this is at cross section A. Now, you calculate the buoyancy force at cross section B. Now, buoyancy force at cross section B, you write like this, this is minus rho g Z A, and you have to actually it is at a higher elevation. So, there will be, you have to subtract another term. So, rho g A dz. Now, here actually you remember that the sign of dz is opposite to that of A, otherwise you will get a larger hydrostatic pressure at B. So, for convenience of your calculation later on you will find that you take the hydrostatic force occurring at B in this form. So, this is your buoyancy force at B, buoyancy or hydrostatic force. Sorry, you do not write buoyancy, you write hydrostatic force. So, this is your hydrostatic force at B. Now, what will be your direction of the hydrostatic force? At end A, your hydrostatic force will act in this direction. This one I am writing. And here what will happen? Hydrostatic force is nothing but the pressure of water acting at this point. What is the pressure of water, in which direction it will act? So, it will act in this direction. So, this is your this force. Now, you do the take the components of these forces in the x and y direction. Now, you take, say you take t plus d component along the tangential direction. So, after this, take components of forces along tangential and normal directions. So, what is the component along the tangential direction? First, let us try to do our tangential direction or tangential component. So, tangential is along the cable line. So, what about t plus dt? So, you look at this diagram. So, if you take the positive direction along the upward line, upward direction. So, this is t plus dt cos how much? T plus dt cos d phi. So, that is I am taking component along this t direction. So, you take only t plus dt cos of d phi, but do not take cos of d phi out here. So, this is acting in the upward direction you take as positive, and if you take the opposite t here, actually your tension is occurring in the reverse direction. So, this will be minus t. Now, you take the component of the buoyancy forces. So, buoyancy forces out here is along this minus rho g z a. So, this is acting in the opposite direction to t. So, here you add. So, minus of minus sign is coming because of this z. So, this will be plus rho g z a. Now, you do this, the buoyancy, these two forces, how much in what direction it will happen. So, this is actually acting in the same direction of t, is not it? in which direction it is acting. This will act in the normal, isn't it? This is your normal line. So, obviously, you have to take a component on this line, that is you have to take cos of d phi, but you do not reverse the sign, it will be acting in the same direction of t. So, here, so you remember these signs, otherwise there will be a problem. So, this will be minus rho g z a, this you simply multiply this by cos d phi, and also the other term, this is minus rho g a d z cos d phi. So, here actually I have changed the direction of this minus rho g z because it is acting on the opposite to t. Here it is along the line towards the direction of t. Only thing is you have to take the component, that is you multiply it by cos d phi, because this is acting on the direction of t plus dt. Your t plus dt is the normal to the sectional area. Followed? Now, what are the other forces? The other forces are your this F, D and weight. Now, weight W is your net weight. So, this angle is how much? This angle, if you write, this is phi. Now, you take the components. So, if you take the components, in which direction this is going to act? So, W d s, there will be two forces, W d s cos phi and W d s sin phi. You take component along the normal, that is along the direction of your drag force. So, that will be W d s sin phi, and along this your W d s is acting vertically downwards, and your angle is how much? This is your phi angle. Now, here along the line of t, this will be how much? So, we are resolving our forces along the line of t and perpendicular to t. So, this will be W d s cos phi, and this one will be W d s sin phi. Now, you tell me the directions. So, W d s cos phi, sorry, this is W d s. So, this will be cos phi, if this is your phi angle, and this one will be sin phi. Now, what? Tell me the directions. So, W d s sin phi will be, it is in the same direction of this t. So, I am just writing your arrows like this, but t we have taken this as negative. So, this will be minus W d s sin phi, and tell me the other force. So, this is coming from the weight of the chain cable. Now, other force is the hydrodynamic component. Now, hydrodynamic component, which one you will take, D or F? So, F is, you assume F to be acting in the direction of T to make matters simple, and D is normal. So, obviously, component of D along the tangent will be 0, isn't it? Cos 90 degree is 0. So, the only force that you are acting is F. So, what is now F is acting in which direction? So, this sign of the forces you be careful. So, F is acting in the direction of t plus dt. So, this will be plus. In our equation this will be, since we have taken the t plus dt to be positive, it is acting in the same direction of t plus dt. So, this has to be taken as positive. But F, we have denoted F as what? This is hydrodynamic force per unit length. It is not the total force. So, it is force per unit length. So, you multiply by the total length of the chain cable for that element. So, what is that length? That is ds plus which one? Yeah. Weight we have taken along the line of t.
That was also per unit length.
Yeah, yeah, that is why I multiplied by ds. This ds. Yeah. So anyway, so F multiplied by ds plus the extension of the length. So this is t over AE. So later on, actually we will neglect this F. So all this trouble that we are taking will go waste. So this is your actual equation. So this is equal to how much? Any other forces left? So this is your first equation, this is your tangential component. Now this d phi angle for d phi very small, d phi is let us suppose change in the angle along this elemental length, d phi is small. What is the value of cos d phi? Cos d phi is very near to 1. So now WDS, here actually this will be another S out here, sin phi. So now what will be this equation? So this will be simply t plus dt minus t. So your t cancels out. And what will be the equation for this? This will be plus rho g z a, and this one will be minus rho g z a. So your rho g z a one, it will go out, and you are left with only minus rho g a dz. On the other side you will get w ds sin phi. And the minus sign will come out here. So minus f multiplied by ds plus TAE ds. So from this equation your t and t will go, and this term will also go. So we are left with dt minus rho g a dz. So this will be equal to w ds sin phi. You neglect f. Now this equation you can write in differential form. You write in differential form, this will be d of T minus rho G A. This will be W sin phi ds. So this is one equation we can get. We are making lot of assumptions. Oh, achha, achha. This will be Z, no? Oh, achha. This is AZ. The AZ I have left out or what? Yeah, so you are taking D, so that's all right. You take the differential, it will be d of dt, and this is d of dt. Now you take the normal component. Now here actually what you are saying that ds I have not multiplied by ds plus TAE ds. That weight per unit length is quite small, that's why this term I have neglected for this case. If you are taking ds plus this all this trouble, but for W you are not taking, isn't it? That is what you are asking. Anyway, so now you get another equation from the normal component. That means you are taking normal to T. So you find out what is your T plus dt. You go. So T plus dt cos phi or sin phi? Sin d phi. What are the other forces? So you look at your free body diagram. So T plus dt cos phi will be along the direction of T. T plus dt sin phi will be on the this direction. Upward direction you take as positive. Now what about T? T is all you're taking component along T, so T along the normal side will be 0. So that is cos 90 degree. So fortunately we are not having any T component. Now you just take the components of the hydrostatic pressure. So hydrostatic pressure you take only this one at the top, because your rho g ZA is along the direction of T. So this red arrow. So if you take component on the perpendicular direction, it will be 0. But here this is acting along T plus dt. This rho g minus rho g ZA and this minus rho g A dz, this is acting along T plus dt. So that is not along the direction. So component along the tangential direction will be cos of this, and the other one will be you simply take sine of this thing. Sine of this thing will be acting in which direction, upward or downwards? Downwards, in the direction of D, isn't it? So minus rho g, you take the component, this will be sine d phi. and minus rho g a dz sine d phi. And this will be, you take the weight component, will be in the direction of d. So, this will be minus w ds cos phi, and this also will be, the drag component will be minus d. This will be how much? You multiply by the total length of the cable. So, this is ds plus TAE multiplied by ds. So, this will be equal to 0. And now you simplify, that's all. Now, here you take d phi for small d phi. You take sine d phi almost same as d phi. With that you make the simplification.
Sir, hydrostatic component will be positive. Plus downwards and sine will be plus.
Sir, W should be positive, W and D. No, sir, upward is taking.
W and
Upward positive. T plus dt इधर लग रहा है.
Sir, T plus dt is upwards.
क्यों?
no, this t plus dt sine d phi you are taking as positive, isn't it?
Upwards is
So, that means the, in this your sine component, in this direction it will be, this is your direction of what? T plus dt sine d phi.
By taking upward as positive.
If this direction you take as positive, then this hydrostatic will be in the opposite direction, isn't it? But then why he has taken this as negative?
Sir, that will be upward, sir.
The hydrostatic, no?
Sir, it will be the hydrostatic is in the similar manner. Same direction as T plus dt into sine d phi.
Sure.
Resolving force.
Yeah, I think this will be in the upward direction, isn't it? The upward direction it will be the same as t plus dt sine d phi. So then this thing remains the same. So now if we make the simplification, then what is happening? So if you make simplification, so this will be t plus dt. Instead of sine d phi, you write d phi. So here this will be minus rho g z a d phi, and this will be minus rho g a dz dz sin, instead of sin d phi you write d phi. And on the other side, how much we are getting? So this will be w ds cos phi plus d of ds plus t over a ds. For now this you neglect. In this term we are neglecting the hydrodynamic forces because we have neglected that other one f, and this one also you take this as equal to 0 because dz multiplied by d phi are two small quantities, so they will vanish. So we are left with t d phi. This will be t multiplied by d phi, because again we are getting small quantity as dt d phi. So all these small quantities you ignore. So minus rho g z a d phi. This will be equal to w ds cos phi. So this one again you ignore. So this is, we are getting t minus rho g z a multiplied by d phi. This is equals to w ds cos phi. So this we are getting from equation 2, the normal direction. Now you can simplify this further. Now you put this t prime is equals to t minus rho g a z. So then we have d of t prime is equals to w multiplied by sin phi ds, and the other one, this is from 1, and from 2 how much you are getting? Simply t prime d phi. This is equals to w ds cos phi. So this we are getting from 2. Now you divide. Now if you divide, you get dt prime over t prime, and what is coming out here? So w ds will go. So we are getting sin phi of over cos phi, that is tan phi. This multiplied by d phi. So we are getting this equation. Now you integrate. So you, after you integrate, you put the boundary conditions, then you will get another equation. Now from that equation you can calculate what is going to be your ds, or length of chain cable. So next class we will do this, calculate length of chain cable. So these are equation of the catenary. The only problem is the sign conventions.